Well, let's give it a shot. Analysis of variance. This will be a very introductory video. So I'm going to be talking mainly at a very high level. We're not going to get into specific examples and that sort of thing. It's meant mainly for people who are struggling with the concept of ANOVA, or maybe just coming across it for the very first time. I'm going to try to break it down for you enough and slowly enough that hopefully you'll understand a little bit better what's going on. All right. So when we think about data in any sort of situation where you're going to be using ANOVA, the data is highly variable, meaning that you have lots of observations, and those observations have lots of different values, different numbers. They're not all the same. So variability like that in data comes from a lot of different sources, but you can think of them as falling into two real main categories. One is real differences between members of the set that you're measuring. So in other words, the numbers in your data set are different because the observations in your data set are different from each other. Whether you're observing people or pigeons or geographic areas, whatever it is that you have measured, there's real differences. And so when you go to measure that, whatever your dependent variable is, your numbers come out different. And then there's also measurement error. That is, when you go to measure something, measurements are never perfect. And so there's always some degree of mush or error in the measurement. And that also leads to variability in your data. All right, so given that, imagine this. You take two samples from the same population and you compute their sample means. Now you have a population and it's got a population mean, right? Remember from my one-hit video, the statistical symbols video, that mu typically we're going to use to represent a population parameter, and we're going to use either m or x bar to represent a sample mean. So we have our population. It has a certain mean, mu, and we're going to take a sample from that population. So, I'm just representing here kind of a random sample. You're going to get a few observations from over here, a few from here, a few from here, and you add them all up and you calculate a sample mean, x bar. And of course, x bar doesn't exactly equal mu. And why doesn't it equal mu? Well, because of measurement error, and specifically in this case, what we call sampling error. That is, when you take a random sample from a population, you don't get exactly equal representation across the entire distribution, right? It's random representation, and so the sample mean will not exactly equal the population mean. And I think that's pretty intuitive for most people. And now we take a second sample, and it will have its own sample mean, which will represent here x bar 2. And of course, once again, its sample mean does not exactly equal the population mean, and it also doesn't exactly equal the other sample mean, right? So we get variability among the sample means when we're taking multiple samples from a population. All right. So each of the samples has its own sample variability, and those sample variabilities, of course, are estimates of the population variability, plus some measurement error. The sample means themselves are also variable. So again, why aren't the sample means exactly the same? Well, because of the population variability. If everyone in the population were the same, the sample means would also be identical. So the variability of the sample means is also an estimate of the population variability. The more variable the sample means, the more variable the population samples come from. The more variable the population the samples came from. If we take 100 samples and compute 100 sample means, the variability in those sample means would be a pretty good estimate of the population variability. Now, there is a little bit of a caveat to that. Won't the sample means be closer on average to the population mean with bigger samples? Well, of course they will. So to estimate population variability, and I'm using variability as just, that's in reference to the fact that all the numbers aren't the same, and of course we have specific measures of variability, like the sums of squares or the variance or the standard deviation. So to estimate the population variability, we have to undo the averaging that goes into the sample by multiplying by n the sample size, how big our sample is. So instead of dividing by n like we do when we compute the mean, we're multiplying by n to undo that averaging to put our estimate of variability back into terms of the variability of the population. So that's, again, because the variability in the sampling distribution of the mean is actually equal to the population variability divided by n, actually some function of n. For the actual statistic sampling, or the standard error of the mean, it's the square root of n. But we don't need to worry about that. That's a complication now. Just in general, you know that this is just a reflection of the fact that our sample estimates get better the bigger our sample is. So to make those estimates reflect more the population variability, we have to undo that averaging. Okay, so now let's imagine a slightly different scenario. Instead of taking 2 samples from a single population, we want to take 2 samples from 2 populations, 1 sample from each of the populations. So I have 2 populations down there with their respective population means, right? mu1 and mu2, population means for my 2 populations. Then I take 2 samples, and each sample has its own sample mean. And in each case, the sample mean is not exactly equal to the population mean of the population we sampled from, but it is an estimate of that population mean. And it's a fairly good estimate, usually. If our sampling, if our method of sampling is good, then our sample means will be a pretty good estimate of the population mean. They won't be too far away. And most importantly, the sample means will be unbiased estimates of the population means. In other words, we're just as likely to get a slight overestimate as a slight underestimate, and so on. Okay. So, yes, I've already mentioned this. Notice how neither sample mean is exactly equal to the population mean, and that is, again, because of sampling error, the fact that we're randomly sampling. And once again, there is variability between the sample means. So the sample means aren't exactly equal to each other, as was the case when we took 2 samples out of the same population. But now, there's a new reason for that. There's a new reason that the 2 sample means aren't exactly equal to each other, and that is because they come from 2 actual different populations. So the fact that the population means are different from each other is also causing the sample means to be different from each other. So now imagine our classic 2-group experiment. We want to know if we're sampling from a single population, and that's the same as saying that our independent variable does not have any effect on our dependent variable, or if we're sampling from 2 different populations. And that's the same thing as saying our independent variable causes a change in the dependent variable. Well, which situation are we in? Of course, we can never know for sure, but we can obtain 2 independent estimates of population variance, and then use those estimates to see if it's more likely that we're sampling 2 samples from the same population, or in other words, our independent variable has no effect, or if we actually have 2 samples from 2 different populations, in other words, our independent variable is causing a difference, hence people at one level of the independent variable represent a different population than people at the other level of the independent variable. Or observations, I should be more general. I'm a psychologist, so I default to saying people when I talk about observations, but this could be cars, it could be an assembly line process, it could be offenders in a criminal justice situation, it could be pigeons, it could be anything. So we can obtain 2 independent estimates and combine the 2 estimates we get. So first we estimate the variability within each group, and we combine those estimates. So we have 2 groups, and what we're going to do is we're going to look at the difference between each group mean and each observation. And this should look pretty familiar to you, right? This just looks like a sums of squares equation. So we've already done a video on basic descriptive statistics and descriptive statistics of variability. And so this is just a sums of squares. But we have a little subscript here. Instead of just a sample mean, we have a subscript to talk about which sample mean we're referring to, because now we have two samples in this example that I'm giving. We would have two sample means. And so we would just take each individual observation, subtract from it its corresponding sample mean, square that, add up all those numbers, and we get the sums of squares. And we notice another little subscript here, W, that stands for within, because it's the sums of squares within each group. Okay, now this here is also new, relatively new. You might have seen the DF before. The DF stands for degrees of freedom, and the W here again just stands for within, just like it did up here. So this is the degrees of freedom within groups, and that just equals the big N. That's the total number of observations in both groups put together. So if you have 10 in one group and 10 in another, your big N would be 20. And K, that's just the number of groups. In the example that we're doing right now, it would just be 2. But the thing about ANOVA, I'll get to this in a few slides, is that we're not limited to just 2 groups, which is sort of why we do ANOVA a lot, rather than just always using t-tests. The t-test is limited to the 2 groups. Okay. So notice how all we're doing really is just combining sums of squares for each group individually. We just add those up, and then we divide by those degrees of freedom to come up with an estimate, an overall estimate of the sums of squares for the population. So it's an estimate of population variability, plus, of course, whatever extra variability we get through measurement error. All right, now that's one estimate of population variance. We're going to get a second estimate in this situation, and that comes from that variability among the sample means. So now we have another sums of squares, but now instead of within, there's a B here. That B is for between group. So now we're talking about the variability between the groups, that is the variability of the sample means. Right here you can see we're going to multiply this estimate by little n. That's the sample size of each individual group. Now this equation will only work if your groups all have the same size. If they don't have the same size, you just have to use the individual n for each group as you're doing this computation. But anyway, we don't need to get that complicated right now. Just conceptually, that is that anti-averaging that I was talking about, that getting this number back into units of the variability in the population. And here again, you just see that we're taking a mean and subtracting it from something, but the thing we're subtracting it from this time is another mean. In fact, it's the mean we saw right here, the group mean. So for each group gets its own mean. So let's just, let me scroll up here a little bit to here. These are the 2 group means in the example that we're talking about right now. X bar 1, X bar 2, that little 1 and 2, that's the sub G in those equations. So back here, we're taking each group mean, and now this is a capital G. I know it's a little confusing. We have little g for the group means, so this would be X bar 1 and X bar 2. Big G stands for grand mean. So X bar sub big G, that is the grand mean. That's the mean of all of our observations, regardless of which group they're in. So we're going to take the distance of each sample mean from the corresponding, or from the one group mean. We're going to square that difference and add those all up, multiply by the sample size for each group, and that gives us another estimate of the population sums of squares. Divide that by the degrees of freedom, which is now just the number of groups we have, minus 1, and that gives us our mean square between, also called the between group variance estimate, and that is just going to be the sums of squares scaled by the degrees of freedom again. So, again, n is number of subjects in each group, k the number of groups, x bar sub g the mean of the gth group, x bar sub big G the grand mean, and df always degrees of freedom. Now, why are we doing this? Why are we getting two different estimates? This estimate of the population variance and this estimate of the population variance. Well, because this estimate right here is not an estimate of only the population variance. Remember, that's not the only reason in this, if we are in this situation, that's not the only reason that we get a difference between sample means. It's also because we're sampling from two different populations. So this estimate right here, the between group variance, or mean squares between groups, two terms mean exactly the same thing. Between group variance, mean squares between groups, same exact thing. It reflects population variance plus any variance being caused by the independent variable. In other words, by the fact that we are sampling from two different populations. Yep, here I just point out there's that anti-averaging I was talking about. All right. So conceptually, this variance estimate reflects both the variability of the population or populations from which the samples came and also the variability between the populations. In other words, the difference between the population means. If we have two samples from the same population, then this variance between populations is zero, right? There is no variance between populations if we're sampling only from one population. All right. Yeah, and I alluded to this before, but yeah, that formula it only works if all the groups have equal numbers of subjects. It's just slightly more complicated if you have unequal numbers of subjects in each group. Then you just have to carry out a separate term for each group and use its own group size in that anti-averaging calculation. All right, but anyway, don't worry about that. That's a complication. Conceptually, this is what we've got now. The within group variance, that's, remember, S squared, that's variance, W within, so this is the within group variance, estimates sigma, remember that's our symbol for a population parameter, sigma squared, that's the population variance, and I just given it a sub pop there to represent population. So the within group variance estimate estimates only population variance, but the between group variance estimate estimates both population variance and variance caused by the independent variable. Now, I'm using that term caused a little, I'm throwing it around a little too loosely here perhaps. We don't necessarily know whether it was causal or not. All that means is that we're sampling from two different populations, not just one. Okay. So, remember, this is because conceptually, when the IV has an effect, it's essentially causing a change in the population, making it a different population. Think of it this way, just to give you a concrete example to wrap your head around. The population of people who have taken a painkiller is different from the population of people who have not taken a painkiller. Let's say it's for headaches. If we're measuring their level of headache pain, the population of people who have taken a painkiller are going to be a different population than the population of people who have not taken a painkiller in terms of their headache pain. All right. Now, suppose we put these two estimates together into a ratio. So we put between group variance over within group variance. If the independent variable, so conceptually this is what we're doing. We have variance owing, the variance owing to the population, the fact that not everybody in the population is the same, plus any variance being added or attributable to, that's probably a better way to put it than causes, attributable to the independent variable, divided by an estimate of just the population variance. So what would we expect this to be if the independent variable has no effect or has no relationship to the dependent variable? Then we would expect that we just have two estimates of the same population parameter, and so we would expect this ratio to be 1. So if the IV has no effect, that means it will not cause the sample means to move apart. They will be different only because of population variability, and so we expect it to be equal to 1. Now, what happens if the IV, the independent variable, does have an effect? It's adding variability to this between group variance estimate, and so we expect this ratio to get bigger than 1. So the more variability the IV is adding, the bigger this ratio gets. So now we have a statistic. Remember, that's just a number calculated on sample data, and it behaves differently depending on whether we're sampling from the same population or two different populations. If we're sampling from the same population, then we expect it to be close to 1, and we expect it to just randomly vary around 1. But we expect it to be pretty close to 1 because we just have two estimates of the same population parameter. But if we're sampling from two different populations, then we expect this ratio to become larger than 1 systematically the further apart these populations are, because that's an added source of variability. The difference in the populations, that is an added source of variability. Now, of course, it might just be bigger or smaller than 1 by chance, even if we're sampling from just one population. What do we need to know then about this statistic in order to make it an inferential test statistic? Well, think back to, if you haven't already, go watch the video on hypothesis testing, because we talk about exactly what we need to know. We need to know all possible values that this statistic might possibly take in any experiment and the associated probability of getting each one of those values. And that is called the sampling distribution. The sampling distribution of the statistic. So we need to know the sampling distribution of the ratio of the between groups variance to the within groups variance. And just again to reiterate, in other words, when we say the sampling distribution of the statistic, the set of all possible outcomes of computing this statistic, that is, all the possible values it might take, if we were indeed sampling from just one population. This will tell us the probability of obtaining a ratio as big or bigger than the one we actually got, strictly by chance. And it turns out that this statistic is distributed like this. We call it the F distribution. I believe it is named for Fisher. I could be wrong about that, historically speaking, but I'm pretty sure it's called F because Fisher came up with it first, or at least maybe did the most thorough documentation of it. So it's called the F distribution. And actually, you can see that it's not a single distribution. It's a family of distributions, just like the t-test was. And the statistic we either call the F ratio or the F statistic. So the x-axis here represents values of the statistic, so values of that ratio. And the area under the curve, technically speaking, because this is a continuous distribution, so the area under the curve represents the probability of getting each of these F values, or one within a range, given chance. In other words, given that we are just sampling from a single population. So in that way, it works just like a normal distribution, but this one, the F distribution, has two sets of degrees of freedom associated with it. One for the numerator of the ratio, that was the between group variance estimate, and one for the denominator of the ratio, that within group variance estimate. And you can see here I've got the two F distributions that I'm showing here, two different sets of degrees of freedom. So this blue curve has 10 degrees of freedom associated with the numerator and only 2 associated with the denominator. And the red curve reversed, well, not reversed perfectly, but 5 and 10 to make these two distributions. F distributions with only one denominator degree of freedom actually look pretty ugly, but these are two nice looking distributions. You can see one difference between this and the normal, or the t for that matter. F distributions are not symmetric. They're not symmetric about their mean, so it's more like the chi-square distribution in that sense. Okay, so now to determine the probability of getting an F as big or bigger than the one we actually get in a given experiment, we can look at an F table. That's pretty old-fashioned. Much more commonly, we're just going to get that probability from a statistical program that is going to do some sort of integration of that continuous curve. All right, and so here's all the equations that we just went over, and then just one little new thing here, the actual F distribution, and of course these two expressions right here are completely equivalent. Again, variance and mean squares is the same thing. And so these are just two ways of symbolizing the exact same ratio. The between group variance over the within group variance, or the mean squares between groups over the mean squares within groups. Exact same concept. All right, so this set of equations for the K is for something called the K independent samples design. And it's called a one-way, this set of equations is called a one-way between subjects analysis of variance. And we almost always abbreviate that ANOVA, analysis of variance, ANOVA. Now, don't worry too much about what each equation means right now. We've sort of gone over it earlier, but right now I just want you to get the concept that what we're doing is getting two independent estimates of population variability, but one of those estimates also estimates variability accounted for by the independent variable, and that gives us a means of testing whether or not we actually have separation of populations, or if we're just taking multiple samples from the same population. Another way of saying, does our independent variable have an effect? Now, I'll do another video where I go step by step through a hand computation example of ANOVA, of a between subjects ANOVA and a within subjects ANOVA, to make sure that you understand the equations. But for now, just understand the concept. It's called between subjects because the between group variance estimate comes from different subjects, so or different observations. So it represents a difference between subjects caused by both the IV and the otherwise natural difference between subjects, i.e. the population variability and measurement error. Now you might be asking yourself, the example that we talked about was for sampling two groups, but we already have a way to tell if two groups are different. The t-test, right? So why do we need the f-test? Well, the reason is this. Just notice in these equations that you aren't limited to two groups. You can use these equations to see if any number of groups are different from each other, although it does introduce some complications that we'll get into in future videos about telling which groups are different from which other groups, that sort of thing. Yes, that becomes more complicated. But more in general, you can just use this to tell as many groups as you've got, are there any differences among these groups? All right, so it gets a little bit more subtle than that, but that's the gist of it. Okay, and that's enough for now. It's already been a very long video, but ANOVA and the f-test are a little bit more advanced than the t-test or the z-test, so I wanted to take some time to unpack it more or less slowly. I remember being in stats classes where the professor said everything once, and that was it. She expected everyone to understand it, even though we were still struggling maybe with understanding what a distribution even was. So hopefully this more expansive approach is helpful to you if you're just getting into ANOVA. I'll get into more of the subtleties and complications in future vids, but for now, see you later. Cheers. Hey, we came in a little under 30 minutes. How about that?